Okay, in this example, we're going to move the center of our Taylor polynomial to 1. That's going to change our setup a little bit. Here we'll have to adjust for that in our polynomial by setting the polynomial term shifted to the right, in this case, by 1, x minus a. So to set up my Taylor polynomial for the function 1 over x squared, I'm going to take a series of derivatives, and I'm also taking a pretty small Taylor polynomial here. I'm taking t2. So my first derivative using the power rule is negative 2x to the negative 3. Bringing that down, I get 6x to the negative 4 for my second derivative. Now here I'm centering at 1, so I'm plugging in 1 to each of these polynomial terms, and my coefficient numerators come out to be 1, negative 2, and 6. So plugging that into my partial Taylor series sum, or my Taylor polynomial, I have my Taylor coefficient centered at 1, so x minus 1 in my polynomial term, my first and my second coefficients. So reducing this, I get 1 over 0 factorial, or just 1. Here I get negative 2 over 1 factorial, or negative 2. And here I get 6 over 2 factorial, which gives me this 3. Now, this is a good estimator, a reasonable estimator, as long as we pick values that are close to this 1, because that's where we've centered it. So I kind of want to just show you what that looks like before we go any further. Here in my grapher, I went ahead and there's my function, the reciprocal function 1 over x squared, one of the reciprocal functions, and then I went ahead and put my Taylor polynomial. I'll show you my window. I set my window from 0 to 2 because this is centered at 1, and so it's really only a good estimator near there. And then I just picked negative 4 and 4 for the y's. And so here is part of that function 1 over x squared. Oh, maybe I should do those guys there, okay. There's 1 over x squared. And there's our polynomial. So remember, I set this to be 0 and 2, so this is about 1 right here in the center of my grapher, and they coincide pretty well right here. But then we can see not too far out, I only picked t2, I start to introduce some error, some difference between the value on the polynomial and the value on the 1 over x squared function, and similarly over here. So we've got to stick around 1 if we want to use this guy as an estimator. So what we're going to try and estimate is 0.95. So that's reasonably close to 1. So we might try and estimate this value by plugging it into my Taylor polynomial. So everywhere I see an x, I'm putting this 0.95, and I just went ahead and plugged all of this into my calculator, and I got 1.1075. Now we're going to estimate the error there, but first what I want to do is just see what the calculator says for 0.95 to the negative 2. $1.1080. So compared to our estimate, looks like we already have some error out there in the third decimal spot. Now we chose a pretty small Taylor polynomial, so it shouldn't be too surprising that it's not a great estimator. But Taylor came up with a way to describe how good his estimates were, and to do this, he created his own threshold for error and defined that using something called Taylor's inequality. Now the proof for this is in your textbook, but what I want to show you is kind of the practical way to use it. So Taylor figured out that the maximum error, or the remainder for the rest of the series, by choosing a certain Taylor polynomial, is bounded by some constant m over n plus 1 factorial times the distance between x and a to the n plus 1 power. Now this constant m here, he found comes from the next function's derivative. And what we're going to do is kind of define how can we find this m, and then how do we describe this distance here, the distance from the center for the threshold that we are using. So for this particular example, we're going to find out how good our estimate is if we stay within 1/10 of 1, right? So between 0.9 and 1.1, what happens? So in order to plug everything into Taylor's inequality, we've got to find this m first. So we're going to go ahead and use the third derivative because we are using a second degree Taylor polynomial. So we have to have our 3 factorial, our 3 up here, and our third derivative. So we just did the second derivative, do you remember, up here? So our third derivative using the power rule is negative 24x to the negative 5. Now this is an increasing function. but it's also negative. So what we want to do is kind of test both endpoints. What's happening when x equals 0.9 and what's happening when x equals 1.1? After we do that, we want to see which one is greater in absolute value, because we want this m to represent the maximum distance, or the biggest possible error. So what I did is I took 0.9 and I took 1.1 and I plugged it into this third derivative in my calculator. And when I plugged in 0.9, I got negative 40.644. And when I plugged in 1.1, I got negative 14.902. This is not too surprising because this function's increasing in this interval, and so we have a large negative number and a smaller negative number. But we want to define m to be the largest of those two in absolute value. So we choose this 0.9 value in this derivative to represent m, because we're trying to give the maximum error here. Okay, so now the last thing we have to consider is where this x minus 1 lives. And we know x is between, 0.9 and 1.1, so I want to know about x minus 1. So I'll take this inequality, I'm going to subtract 1, subtract 1, subtract 1, and when I do that, I get here negative 0.1 is less than x minus 1 is less than 0.1. Now this makes sense, right, because we're centering at 1, and we already can kind of see that this is 1/10 away from 1, the center. But what we want is to realize then that our x minus 1 value here in absolute value is bounded by 0.1 in either direction. So these are the two pieces that we need. We need this guy for m, the third derivative at 0.9, and then we need this value 0.1 for this x minus 1 category in Taylor's inequality. So you can see here that I plugged that in. Here's the m, the third derivative at 0.9, the larger of the two in absolute value, divided by 3 factorial, multiplied by this distance from our center, 0.1, the maximum distance from the center, cubed. Putting that in, I get that my error does occur here in the third decimal spot, but this would be the maximum error, or the maximum difference between the true sum and ours. So it's not surprising here that we ran into error at the third decimal place. We chose a relatively small Taylor polynomial. If we wanted a better estimate, we would need to add some terms here, and then I think we would do a little bit better. So here's an example of how we can still estimate a function's value even if we shift our polynomial. Our polynomial shifted right 1 here. It's still a good estimator as long as we stay near this a value, this 1 value.